Hi, here's the problem on compactness of stats. So here we're given two functions f and g. F of x1 comma x2 is defined by x1 square plus x2 square minus 2x1 x2, but this is nothing but x1 minus x2 whole square. Okay. Next we have function g, which is given by this expression 2x1 square plus 2x2 square minus x1 x2. Now we're given two statements, S1 and S2. S1 is for every compact subset of R, inverse image of K under F is compact. And statement S2 is same statement as S1, except that instead of F, we have G. So let's investigate which of these statements, S1 and S2, is actually correct. So we have to pick the correct segment out of S1 and S2. Okay. So let's see how to solve this. So we know that by Heinz theorem, this is the theorem that we'll be using to solve this. So Heinz theorem says in Euclidean space Rn, a set A is compact if and only if A is closed and bounded. Okay. So we're going to use this statement. So let's take S1. So for S1, it says that for every compact subset of R, F inverse of K is compact. Is this true? Well, if I take K to be the singleton set 0, then what is F inverse K? Well, in this case, F inverse K is the set of all x comma y in R2 such that F of x comma y is in K. But here, K is the singleton set 0, so we get x minus y whole square equal to 0. And this happens precisely when x is equal to y. So here we have x comma x are doing such that x is in R. And what is this? This is nothing but the line passing through the origin. This is the line y equal to x. This is our f inverse k. So is it bounded? It's not bounded, right? Because there doesn't exist any ball of any radius r which contains this entire set y equal to x. You take this ball and still you have some parts of this line which are outside this circle, right? So we can't bound this set, therefore this set is not bounded, and therefore f inverse k doesn't have to be bounded for every compact set k. So by Heinz-Gödel theorem, which says that is bounded and closed, then it is compact, we can say that f inverse k doesn't have to be compact, right? So statement S1 is false. What about statement S2? So let's investigate S2 now. Well, here you can see that G inverse K is closed. Why is it closed? Well, take any sequence in G inverse K such that this sequence converges. Converges from X comma Y. Now, to show that G inverse K is closed, all we have to do is to show that this X comma Y lies inside G inverse of K. But what this means is that G of X comma Y is inside of K. That means twice of x squared plus y squared minus xy lies inside of K. So let's do that. Since xn yn is inside G inverse of K, it follows that G of xn comma yn lie inside of K. And G of xn comma yn is nothing but twice of xn squared plus yn squared minus xn times yn inside of K. And this converges to twice of x squared plus y squared minus xy. Now, note that this is a sequence inside K. So here is a sequence inside of K, and K is compact, right? And since K is compact, it has to be closed by Heisenberg's theorem. K is closed. So where will this limit point lie? Will be the limit of this sequence lie? It will lie inside K because of closeness. So x squared plus y squared minus xy lies inside K. But this is nothing but g of x comma y, which means that xy is in the inverse image of K under G. And that's precisely what we set out to prove. So we have shown that. So G inverse K is closed. So we're about 50% done. Now, if we could show that G inverse K is bounded as well, then we'll be done. We'll be done 100%. So let's do that. So here I claim that G inverse K is bounded. Okay. So since K is bounded, we know that there exists some alpha such that for every y in K, mod of y has to be less than alpha, right? Okay. Now, to show that G inverse K is bounded, so G inverse K is a set in R2 that is plain. Let's say this is my G inverse K. To show that it is bounded, what I have to do is to show that there exists a ball which contains all of it, right? That means there exists an R such that G inverse of K is contained in a ball centered at the origin and having radius R. If you want to simplify it further, you can say that for every A comma B inside of G inverse K, A comma B lies inside the open ball B0R. And what this means is that A squared plus B squared less than R. Okay. Now, to see this, taken C comma D inside G inverse of K. But this means that twice of C inverse plus T inverse minus CD is inside of K. And we know by arithmetic mean greater or equal to geometric mean inequality that C square plus D square upon 2 has to be greater or equal to twice of mod CD. And this quantity is less or equal, is greater or equal to twice of C square plus D square minus mod of CD, right? Because negative of mod CD is less or equal to 30. So we have this here, and oh wait, I made some mistake here. So since this is inside K, we can say that this is less than alpha, right? Because K is bounded. K is bounded. K is bounded, so there exists an alpha. So this is less than alpha, and because of this, this is now less than alpha. Now we can use the AM greater than or equal to GM inequality here to get 2C square plus D square is C square plus D square over 4, right? This is less than alpha. So what do I have here? 7 upon 4, C square plus D square less than alpha, C square plus D square less than 4 upon 7 alpha. I can choose this to be my R, right? So that means CD is inside ball centered at 0 having radius R. And this is true for any arbitrary point inside G inverse of K. So we can say that G inverse of K lies completely inside B0R. So G inverse of K is bounded. So G inverse K is bounded, and we have shown earlier that it is closed as well. So bounded. So by Hein-Borel theorem, G inverse K is compact. So this shows that S2 is correct state. Let's do this. Okay, thanks for watching.